Thank you, everybody. I got called to do this paper sort of on short notice, so hopefully it has some interest for you, and we can go from there. The program calls for me talking about RF technology, and I'd like to say RF can be used for, RF obviously stands for radio frequency, and it can be used for three things, really. Communications, which I'll be talking about today. It can also be used for energy. Of course, you can use radio to bring energy to places where you couldn't have it normally. And finally, you can use RF to sense things that are going on. And I won't be talking about those, but there are other applications for RF. I'll be talking about wireless. And I get this working here. So the questions I have for using communications, the questions are, which wireless, first of all, do you need wireless? Which wireless technology to use? What applications are required for that? What are the physical limitations of wireless technologies, and how do they impact your design? Because you're using a shared resource, the spectrum, there's regulatory requirements that have to be taken into account. Finally, of course, you have to worry about the economics of it. There's always a solution, but sometimes it's too expensive. I'll give a couple of examples, and then I'll open it up for questions. So the first question is, why would you actually want to use wireless? And let's see, there we go. Really, in many cases, wired communications is better than wireless technology. If you actually can run wire there, it has a lot of benefits in terms of security, in terms of the ability to handle large amounts of communications capabilities. Where wireless does shine is if you have to move around. If you have to change things. It can be a lot cheaper, especially if you're using an existing plant, for example, and you want to put in a new communication system. To run wire in an existing facility is extremely problematic, and wireless can be a good help there. Wireless can help if you're reliant on third parties to access, that could potentially access information that's confidential. You can sort of bypass some of that by having your own wireless system. It can be safer in many cases because you don't have to bring people to places where they could be put in harm's way. That would be the biggest reason. And sometimes it's just nice to be sexy about it and say, I have a new wireless system, and it's the marketing guys want it. Really, there's no economic or technological advantage to it. So the next question, of course, is if I am going to use wireless, what's the best wireless technology to use? And really, it boils down to you have to have one that meets your requirements and that you can afford. And so we'll talk a little bit about what those requirements are and what the economic and physical limitations are and the regulatory issues. So the first question is, what do you want to do with the wireless system? And that's where we have, does it have to carry voice? Does it data? Both? How much data, if it's going to be data? How much data do you have to feed through the system? What kind of structure is it? Is it continuous? Is it bursty? Is it sporadic? Once a week, once a month, every millisecond? How far do you have to go? And what are the impediments between where you're starting and where you end up? Is it in a mountainous environment? Is it in going over water? Is it in a building? All these aspects have to be taken into account when you're choosing a wireless system. The network topology, is it going to be point-to-point? Is it going to be point-to-multipoint? Is it going to be multipoint to multipoint, like in a mesh? Is it going to be ad hoc? Is it going to be changing all the time, or is it going to be a fixed process that you sort of know what you're getting yourself into, and you can choose a different system in that case? And is it going to be self-contained, or is it going to be part of a bigger communication system where I just have a wireless link that provides part of the overall structure, but I'm still using other technologies that I have to be compatible with? Other questions to ask are quality of service. And quality of service in a telecom definition means how reliable is the service? Am I going to get what the telcos strive for? They call it 5 nines, 99.999% availability of the system. Or do I need that? It's going to require a different kind of solution than if I can get some of the parts coming through some of the time. Security and integrity are important issues, especially if you're dealing with confidential or information. Is it easy to listen in on what's going on? You might choose a different topology or technology than if it's not. Are you worried about people breaking into your system, either doing a denial of service attack so that you can't transmit your stuff, or pretending to be somebody else that you don't want to have in the system? Again, those questions will, to some extent, define what the best solution for you is. Latency and time accuracy, I'll talk about some examples later on where time accuracy was extremely important for one application, and some technologies just don't give you that time accuracy, so you have to do something different. Environmental factors, of course. If it's up north and it's going to be unattended, it's going to have to work down to very cold temperatures. And likewise, if it's going to be in Saudi Arabia in the summer, it's going to have to work to very warm temperatures, and you have to be able to deal with that. Power consumption, if it's going to be battery powered or solar powered, there's going to be different constraints than if you have unlimited power available. Size can be an issue, and of course, again, safety. If it has to go in an intrinsically safe environment, there's going to be different issues than if you don't have to worry about that. From the physical perspective, generally speaking, the higher you go in frequency, the less range you get. So if range is an issue for you, you want to sort of go down to the lower frequencies, and there's some physical reasons for that. One of the important part of it is the size of the antenna that you can get. If I want to have a big antenna and get lots of gain, at low frequencies it's going to be a huge antenna. At high frequencies it can be a very small antenna. It also has to do with how radio waves interact with the environment. If you're driving over from Calgary to Banff and you're listening to the radio station, on the AM band you can really go all the way from Calgary to Banff itself in the mountains, because the radio waves tend to go around the corners a bit. In the FM band, the radio waves are a bit shorter, and as you go over the top of the hill at Scott Lake there, you start losing your FM signal. If I were to try to do that at UHF, I wouldn't even get that far, because again, the higher you go in frequency, the more line of sight the radio waves become. Multipath is an issue, and multipath affects radio performance in a big way. What that is, if the radio wave bounces off something else, it's going to take a longer path. The propagation of radio waves is the same as propagation of light, and it's about 3 meters per 3 meters per nanosecond. And so as you go in areas where you have a lot of potential, buildings, or you have mountains, or you have other big structures, you can get multipath, which will affect again what kind of radio system you want to choose. Interference is always a big issue, and that can be either man-made. A lot of the unlicensed bands, you're sort of at the mercy of whoever else is in the band there, and interference can be a big issue. It can also be natural. Sunspots can cause interference. Background radiation in the earth can cause interference in some cases. And so, depending on where you operate, you have to take that into account. There's another effect, sort of a physical effect, is that with the modern technologies for modulation, you can get a lot of information in a small bandwidth. The price you pay for that is that the waveforms get very complicated, and they require a lot of linearity, and they require a lot of power to get that through. So in some cases, that again limits. You can get a lot of power, a lot of information through for short distances, but you wouldn't be able to get it through for longer distances.